Here's a question that sounds almost too bold to be true. What if I told you there was a single mathematical object, one thing, that if you knew it completely, you could predict everything a quantum system will ever do? Every energy it can have, every state it can be in, every way it evolves through time. That object exists. Physicists use it every single day, and it has a name, the Hamiltonian. This is a video where we actually understand it, not just what it looks like, but where it came from, what it's doing, and why every quantum computer ever built runs on it. To understand the quantum Hamiltonian, we go back to 1833. An Irish mathematician named William Rowan Hamilton was working on a complete reformulation of Newtonian mechanics. Newton gave you forces, Hamilton wanted energy. His idea was this: instead of asking what force is acting on this particle, ask a different question entirely. What is the total energy of the system? He defined a function, h of q and p, where q is position and p is momentum. These two quantities together completely describe the state of any classical system, and from this single function, he could derive anything. H of q and p equals t plus v. Total energy equals kinetic energy plus potential energy. Simple, but what he did with it was not simple at all. From this function, Hamilton derived two equations that govern how any classical system evolves in time. Derivative q over derivative t equals partial h over partial p. Derivative p over derivative t equals negative partial h over partial q. The rate of change of position equals how the energy varies with momentum. The rate of change of momentum equals a negative how the energy varies with position. These are Newton's laws, completely written in the language of energy. For a harmonic oscillator, a mass on a spring, the Hamiltonian is p squared over 2m plus 1/2 kq squared. Kinetic term plus spring potential. Plug that into Hamilton's equations and you get the equations of motion of a spring automatically. No forces needed, just energy. Here's where everything changes. In classical mechanics, h is a function, p is a number, a definite value you can write down. In quantum mechanics, that is no longer allowed. Heisenberg's uncertainty principle tells us position and momentum cannot be both simultaneously definite. They are not numbers, they are operators, mathematical objects that act on quantum states rather than multiplying them. And if momentum is an operator, then the Hamiltonian, which is built from momentum, must also be an operator. This step is called quantization. We replace classical momentum p with the momentum operator. P hat equals negative I h bar times the partial derivative with respect to x. That substitution, p going to p hat, is one of the most consequential moves in the history of science. It transforms the Hamiltonian from a simple energy function into a different operator that acts on wave functions. The quantum Hamiltonian for a particle in one dimension becomes h hat equals negative h bar squared over 2m times the second spatial derivative plus v of x. The hat means it's an operator now, the same structure as the classical version, kinetic plus potential, but now it's a machine that takes a wave function as input and produces another wave function as output. Once you have the quantum Hamiltonian, one equation governs everything. I h bar times the partial derivative of psi with respect to t equals h hat p psi. I h bar times the partial derivative of psi with respect to t equals h hat psi. This is Schrödinger's equation, and what it's saying is that the Hamiltonian generates time evolution. The left side is how this quantum state changes in time. The right side is the Hamiltonian acting on that state. They're equal. The Hamiltonian drives everything. Now there's a special case. If the Hamiltonian doesn't change in time, the system has constant energy, we can write the time independent form, h hat psi equals e psi. This is an eigenvalue equation. Psi is an eigenstate, which is a wave function with a definite stable energy. E is the eigenvalue, which is the actual energy value you'd measure if you look at the state. The set of all possible E values is called energy spectrum of the system. Every result in quantum mechanics you've ever heard of comes from solving this equation for a specific Hamiltonian. Atomic orbitals, molecular vibrations, the ground state of a quantum computer, all of it is h hat psi equals E psi for different choices of h hat. So let's build intuition by walking through the most important Hamiltonians in quantum physics. Each one is a different choice of potential v of x, and each one gives completely different physics. So the first type, the free particle, which is the simple possible case. No potential, no forces, just a particle drifting through empty space. H hat equals p hat squared over 2m. The eigenstates are plane waves, e to the ikx, and the energy spectrum is continuous. Any value of energy is allowed, no quantization, because there is no confinement, no boundary conditions, nothing to force the wave function into discrete shapes. The free particle is the baseline. It shows you that discrete energy levels are not automatic in quantum mechanics, they require something extra. Now, add confinement and trap the particle between two walls of position 0 and L. The potential is 0 inside. The infinite outside, the particle physically cannot escape. The wave function must be 0 at both walls, and that boundary condition is everything because only certain standing waves fit inside the box, the ones where an integer number of half wavelengths exactly fills the length L. The energy levels are En equals n squared times pi squared h bar squared over 2ml squared. When n equals 1, 2, 3, and so on, discrete, quantized, inevitable. The eigenstates are standing waves, sine functions that fit perfectly inside the box. The first is a half wavelength, the second is a full wavelength, and the nth is n half wavelengths. This is the simplest model that answers the question, where do discrete energy levels come from? They come from confinement. Trap a particle and it can only take certain shapes. Force it into certain shapes and it can have certain energies. That's it. Now for the quantum harmonic oscillator, it's the most important Hamiltonian in all of physics, and it's not an exaggeration because h hat equals p hat squared over 2m plus 1 half m omega squared x squared. Kinetic energy plus a parabolic potential, the quantum version of a spring. This Hamiltonian appears everywhere. Vibrating molecules, electromagnetic field modes, phonons in a crystal, superconducting qubits, the Higgs field. At some level of approximation, almost everything in physics is a quantum harmonic oscillator. The energy levels are En equals h bar omega times the quantity n plus 1 half. Two things jump out immediately. First, the levels are evenly spaced. Each one is exactly h bar omega over the previous. That spacing is fundamental unit of energy for this system. Now, for the ground state, n equals 0, it has energy 1 half h bar omega, not 0. Even at the absolute lowest possible state, the system still has energy. This is 0-point energy and is a direct consequence of Heisenberg's uncertainty principle. You cannot simultaneously know position and momentum precisely enough to put the particle perfectly at rest. It must always be jiggling, even at 0 temperature. The elegant way to work with this Hamiltonian is through ladder operators. We define a creation operator A dagger and annihilation operator A. They do exactly what names suggest. A dagger steps you up the energy ladder and A steps you down. In terms of these operators, the Hamiltonian rewrites beautifully. H hat equals h bar omega times the quantity A dagger A plus 1 half. The operator A dagger A is called the number operator. It counts how many energy quanta are in the state. This ladder operator language is the foundation of quantum field theory, where particles themselves are understood as quanta created and destroyed by operators exactly like these. Now for the hydrogen atom, it has 3 dimensions. An electron in the electric field of a proton. H hat equals p hat squared over 2m electron minus e squared over 5 pi epsilon 0 r. Kinetic energy of the electron minus the Coulomb attraction between the electron and proton separated by distance r. Solving the eigenvalue equation for this Hamiltonian gives the complete structure of the hydrogen atom. The energy eigenvalues are En equals negative 13.6 electron volts divided by n squared. The negative sign means the electron is bound. It takes energy to rip it away from the proton. The ground state at n equals 1 has an energy negative of 13.6 eV, or electron volts. To ionize the atom, you need to supply at least that much. The eigenstates are the atomic orbitals, the SPDF orbitals we've seen in chemistry. They emerge directly from solving this one equation. 3 quantum numbers appear, n for principal, L for angular momentum, ML for magnetic orientation. The entire shell structure of the periodic table is encoded in the eigenvalues and eigenstates of this single Hamiltonian. The wavelengths of spectral lines, the specific colors of light that hydrogen absorbs and emits, are just energy differences between the eigenvalues. En minus Em equals HNU. The Hamiltonian predicts every line in the hydrogen spectrum with extraordinary precision. Now we enter territory that has no classical analog. For a spin half particle, an electron, a qubit, in a magnetic field, the Hamiltonian is h hat equals negative h bar gamma over 2 times the quantity b x sigma x plus by sigma by plus bz sigma z, where gamma is the gyromagnetic ratio, b is the magnetic field vector, and sigma x, sigma y, sigma z are the Pauli matrices. The Pauli matrices are 2x2 matrices that act on the 2-dimensional Hilbert space of a spin half system. Sigma x flips that spin, it's the bit flip. Sigma z shifts the phase, it's the phase flip, and they generate rotations around the x, y, and z axes of the Bloch sphere. When a magnetic field points purely in the z direction, the Hamiltonian becomes negative h bar gamma bz over 2 times sigma z. The eigenstates are to spin up and spin down with energy split by the field. This is a Zeeman effect. A magnetic field breaks the degeneracy between the 2 spin states. This Hamiltonian is the foundation of every qubit in every quantum computer on the planet. A qubit is a controllable 2-level quantum system, and its dynamics are governed by the spin Hamiltonian of exactly this form. When a quantum gate rotates a qubit on the Bloch sphere, it does so by turning on a specific Hamiltonian, applying a pulsar field in the specific direction for a precise amount of time. Now, real systems don't exist in isolation. When two quantum systems interact, two qubits, an atom, and a photon, the total Hamiltonian splits into three parts. H hat total equals H hat system plus H hat environment plus H hat interaction. The interaction term is where all the interesting physics lives. For two coupled qubits, the Heisenberg exchange interaction looks like H hat interaction equals J times the sum of sigma x tensor sigma x plus sigma y tensor sigma y plus sigma z tensor sigma z. J is the coupling strength. The tensor product is the mathematical way of combining two separate Hilbert spaces into one joint system. Control J and you control how strongly the qubits talk to each other. It's the physical mechanism behind every two-qubit gate, and it's exactly how entanglement is generated in real hardware. Now here's the deepest insight. The formal solution to Schrödinger's equation is psi of t equals e to the power of negative I h hat t over h bar times psi of 0. This exponential of the Hamiltonian, called the time evolution operator u of t, takes your initial quantum state and propagates it forward in time. It is unitary, meaning it preserves total probability. The sum of all outcomes always equals 1. If you know the energy, eigenstates, and eigenvalues, you can write any initial state as a superposition, and the time evolution is just an eigenstate picking up a rotating phase factor. Psi of t equals the sum over n of cn times e to the negative I e n t over h bar times the eigenstate en. Each component rotates at its own frequency, proportional to its energy. When these components interfere with each other, you get the rich oscillating dynamical behavior of quantum systems. Atomic transitions, qubit oscillations, molecular vibrations, it's all in this equation. Now, everything we've built directly connects to quantum computing. The Hamiltonian plays two distinct roles. Role 1 is the problem Hamiltonian, also called the cost Hamiltonian. In algorithms like QAOA, which we discovered in our previous video, you encode the optimization problem you want to solve directly into a Hamiltonian. The structure is deliberate. You design HC so that its ground state, its lowest energy state, eigenstate, is the solution to your problem. Finding the ground state is solving the problem. The quantum computer's job is to find it. Role 2 is the mixer Hamiltonian. If the cost Hamiltonian is gravity pulling the system towards good solutions, the mixer Hamiltonian is what prevents it from getting permanently stuck in a local minimum. It generates superposition, drives exploration of the solution space, and physically enables the quantum tunneling that lets the system escape suboptimal configurations. In QAOA, the circuit alternates between these two, applying the cost Hamiltonian for time gamma, then mixer for time beta, repeating the cycle while a classical optimizer tunes those parameters. And this connects to something fundamental. Every quantum gate is an exponentiated Hamiltonian. U equals e to the negative I h hat t over h bar. A single qubit x gate is implemented by turning on h hat equals pi over 2 times sigma x for the right duration. If 2 qubit entangling gate is implemented by turning on the coupling Hamiltonian between two qubits, a complete quantum circuit is at the hardware level a precisely choreographed sequence of Hamiltonians switched on and off in time. The circuit diagram you see in a textbook and the physics happening in the cryostate are connected by this one equation. Let's zoom all the way out. The Hamiltonian is not one equation among many in quantum mechanics. It's the central object. Everything else in the theory derives from it. The energy spectrum of any system, eigenvalues of h hat, the stable quantum states, eigenstates of h hat, the dynamics of quantum state generated by h hat through the Schrödinger equation, the quantum gates in the quantum computer, exponentials of h hat, the atomic orbitals of every element, eigenstats of the respective h hats, the spectral lines of light emitted by atoms, differences between eigenvalues of h hat, the ground state of every material, the lowest eigenstate of that material's h hat. If you can write down the Hamiltonian of a system, you've captured everything there is to know about that system's quantum mechanics. The challenge, and this is where the real work lives in physics, is writing down the right Hamiltonian. Choosing the right approximations, including the terms that matter and dropping the ones that don't, that is the art of quantum physics, and it takes a lifetime to master. William Rowan Hamilton reformulated classical mechanics with a function called energy. A century later, Schrödinger and Heisenberg and Dirac promoted that function to an operator, and in doing so, they found the equation that runs the universe. H hat psi equals E psi. That's it. That's everything. Thanks you for watching. Keep questioning the quantum world, and I'll catch you next time.